Hey, if you missed class or would like a rehash of this last lesson of the year, here it is. First, we talked about exponential growth and decay. Here's an example of exponential growth where each new y value is approximately 138% bigger than it used to be. We know that exponential growth grows really fast. Eventually, the curves usually look like this. And we can see that happening with these numbers. They're starting to grow very fast. All right, the differential equation for exponential growth you should recognize. If a y value is growing exponentially, then its rate of change will be proportional to its current population. Anytime you see this, you know that y is an exponential curve, which looks like this, because when we solve this differential equation by doing separation of variables, we get the standard form of an exponential curve. So recognize these two equations, have them memorized. A quick example, this comes from real life data where y is the number of COVID cases and x is the number of days since case number 1. After 67 days, we had this many cases. After 82 days, 300,000 cases. So another 100,000 in just 11 days, and then just 4 more days to get another 100,000. Seems to be growing exponentially. So this would be its differential equation, and this would be its equation for y. So let's use the first and third values to actually find a model for this curve, y. This is the equation. We need to find two constants, the c and the proportion constant k. So when we substitute the x and y value into this equation, we have our system, and we need to find c and k. Using the substitution method, first I'll use equation 1 and solve for c, rewriting this denominator and the numerator this way. And then we'll substitute this back into the other equation, equation 2. And when we substitute that into equation 2, it goes right there in place of c. This simplifies to 3 equals e to the 15k. So taking the natural log of both sides, we see that k is about 0.073248. Well, now we know k, but we still need to find c. So we'll take this k value and put it into either equation, doesn't matter which. And when we put that value into, let's say, equation 1, goes right there for k. We can easily solve for c. C is about 246, and so the equation is 246-ish times e to the kx power. All right, but in real life, there's often limiting factors like competition for resources. So when things grow exponentially at first, but then they slow down and reach some kind of carrying capacity, a maximum y value, we'll call L for the limit. At that point, the rate of change is 0. It's not getting any bigger, it's not getting any smaller. The rate of change is essentially 0. So coming up with the differential equation for this logistic behavior is basically saying it's going to be exponential mostly, so dy dt equals kp, but eventually we want the rate of change to slow down. And so by subtracting a percentage from 100% of the k rate, the k constant, we're going to slow down this rate of change, just the way the curve shows it. And when y over L is subtracted from 1, as y grows, we're subtracting more and more of a percentage away from the 100% of the k constant, until y approaches L, which means this is approaching, the y value is approaching the maximum, so this is approaching 1, and this is approaching 0, so that the rate of change is approaching 0, just the way we can see in the curve. When it's horizontal, the rate of change is 0. This is the differential equation for logistic curves. We will have that memorized, and we will recognize it whenever we see it. It's been a minority of the times, but the AP Calculus BC test has asked students to solve a differential equation using separation of variables. And if that ends up being on the test this year, you want to be able to do it. So we did it in class. And here's a summary of what that process looked like. First, we do the separation of variables. Y is a factor in terms of y, and this entire difference in parentheses is a factor in terms of y. So we can divide both sides by y times the difference. It'll be on the bottom on the left, and k will be left over. And we'll get the differential of t on the right. Separation of variables complete. Next step. Fraction decomposition. So we want to take this left expression, 1 over this product, and rewrite it as a sum of two different fractions. So we'll do partial fraction decomposition. We should be pretty confident with that process. Letting y equals 0 cancel out this term, allowing us to find a, and letting y equals L will cancel out this term. That would be 1 minus 1 if y becomes L. That would be 0y. So that term will cancel out, and we'll find that b is 1 over L. So we can rewrite this integrand as 1 over y plus 1 over L over that. All right, then we can do the antiderivatives of everybody. First, when you rewrite this term as 1 over L multiplied by this, we'll get L minus y. Then we're doing a u substitution. Be careful there. If u is L minus y, then du is a negative 1 dy. So this expression is actually the integral of a negative 1 over u du. So we can change that to minus the integral of 1 over u. So minus the natural log of u. And then remember, we can flip the order around of L minus y, because with the absolute value, those values will be exactly the same. And we want our variable y to be in front. Then use the property of logarithms, then exponentiate. And at this stage, we needed to get rid of the denominator, multiply both sides times y minus L. Distribute, collect all of your terms with y on the one side, factor out the y, divide by that difference. And once you divide by that difference, we have this black expression. We're going to simplify things by getting rid of this CE to the KT on top. So we'll divide both the top and the bottom by a negative CE to the KT power. That nicely just gives us that. And then 1 times this, we can write the e to the KT, which is in the denominator. We can write it on top with a negative exponent. And it is negative, but negative over 1 over c is just some constant, so we can just treat that as c. And so we'll have 1 plus c e to the negative kt. And that's it. That's the process. You're going to try that in the AP 6 practice questions. This was the general form. In your practice question, it's actually going to be a specific diffie-q that you're solving. So you're actually going to have some values for k and L, but the process will be exactly the same. So get your practice on that. All right, we need to recognize this as a differential equation of a logistic curve. Y is the population, t is time, and there will be the variable y in 2 places, outside the parentheses and on the inside. Sometimes they'll use p for population. It doesn't have to be y, but we need to recognize it like this. All right, look at this form here. We have our constant of proportionality times y times 1 minus y over L. If we actually multiplied this entire difference by L, but then multiply the front by 1 over L, it would be exactly the same. In other words, the inside of the parentheses might look, instead of like 1 minus our variable divided by the max, it might actually say the maximum value, so some number minus the variable y. So if it looked in this, like this form, when you had something, some value times y, and then times like 1200 minus y, then that's an equivalent form of what we developed. And the number in front of the negative sign is the y max. And this isn't quite this value. Let's say this whole value was 0.7 y. That's 0.7 is not our k in this form. It's a little different. So we're going to focus on this form. And if we see a differential equation that instead of having 1 minus this ratio, it has some number minus y, we're going to rewrite it in this form so that we can see the k value and easily just go straight from the differential equation to the explicit function for y. Because we can't do that from here, but we can from here. All right, so we need to recognize that it's a logistic differential equation when the parentheses has a difference of two values, and after the subtraction sign is our variable y for population. And in front, there is some factor multiplied by y. All right, when we solve this, and so hopefully you won't have to because it's a lot of work, we can just go straight from the differential equation to this. The maximum on top divided by 1 plus some constant times e to the negative kt, where k is the k in this logistic diff-eq. So if we end up seeing a diff-eq in this form, we're going to have to do a little work to find out what that k value is. On the next slide, we're going to do an example which deals with exactly that problem. All right. This is the logistic explicit function. Y is a function of t. And we proved by taking the derivative of the derivative and finding the inflection point, which is also the maximum of this derivative, which was when y was changing the fastest. We proved that it's changing the fastest as soon as the population is half of its maximum. And that's something you want to have memorized. This was our proof. Given the diff-eq for population y, we know how fast it's changing. If you want to know when it's changing the fastest, we'll want to know the maximum value of this dy dt. So you'd take the derivative of this and set it equal to 0. So taking the derivative of that is the second derivative. And when we set this equal to 0, we can algebraically get to the value when y is half of the maximum. So that's when this is at its maximum. It's changing the fastest when the population reaches half of its max. All right, we're going to do two nice key examples where in each case, we're going to ask for the limit of the population as time approaches infinity. We're going to ask what y value do we hit when the population is growing the fastest. And we're going to actually ask to find what is the equation for the population if it starts out at 8. All right, when you see this, the y outside the parentheses and then something minus y, it's logistic. As t approaches infinity, our population is approaching its maximum, which is the L value. That's just 400. Since we'll have this memorized, we'll recognize that it matches this form, and 400 is the maximum value. When will it be growing the fastest? When we hit half of the maximum value. And finally, what's the equation? Well, we know that when it's in this form, 2/3 is k, and this value is the y max, which is L. We know that this is the explicit function for population, the maximum value over 1 plus ce to the negative k times t. So to solve for y, we don't need to do the work. We can just say y is the maximum value over 1 plus ce to the negative k value times t. The k value is 2/3. So the opposite of k, t. But we have to find c. So now we're going to use the initial value when x is 0 or when t is 0. The y value is 8. So we put in a 0 for t and an 8 there. This is 0. E to the 0 is 1. So that nicely is just 400 over 1 plus c times 1. Multiplying both sides times 1 plus c, we have 8 plus 8c. And quickly we get that c is 49, and there it is. So we've answered all three questions. Now let's do an example where you might see the diff-EQ in a different form. All right, here we go. Example 2, differential equation. So this doesn't look like 1 minus y over L, but it still has a y out front, and we're still have a number minus y in the parentheses, so it's definitely logistic. So first we're going to rewrite it in the form that we developed in class, which was this. How are we going to do that? We're going to do this green thing, which notice it's just multiplying by 1. 1200 over 1200 is 1, so we're not going to change the value at all, but we're going to distribute the 1200 in front of the parentheses, and the 1 over 1200 is going to get multiplied by the parentheses. And when we do that, inside the parentheses we'll have 1 minus y over 1200. And in front, 1200 times this is 0.444. So now it's in the form that we've developed. We know what the k value is. We know that this is the maximum. And yes, this will always be the maximum when it's written in this form, 1200, but it's not clear what the k value is. So now it is, and now we can do all these questions really quickly and easily. So, as t approaches infinity, the limit of the y is the maximum, 1200. When are we growing the fastest? When y is half of its max, 600. What's the equation? The maximum value over 1 plus c e to the negative k, and k is 0.444 t. We have to find that constant, so we're going to use when t is 0, y is 8, and very quickly we find that c is equal to 149, and we're done.